The moon hangs above Earth every night, calm, familiar, and seemingly well known. But one half of it remains hidden from direct view, and when NASA finally begins to study that unseen far side, the discoveries are astonishing. Ancient crater fields, a colossal basin larger than most imagine, frozen darkness near the poles, and evidence that the moon's hidden hemisphere tells a completely different story from the side facing Earth. This video explores what NASA finds on the moon's far side, and why that hidden world is far stranger and more important than it first appears. Please like the video, subscribe to the channel, and turn on notifications to follow more deep space stories. The moon moves around Earth with a steady patience, and over long spans of time its motion settles into a special balance. It turns on its axis at nearly the same rate that it completes one orbit around Earth. Because of this matched rhythm, one hemisphere faces Earth almost all the time, while the other remains turned away. This condition is called tidal locking. A tide, in this sense, is the stretching effect caused by gravity. Over immense ages, Earth's gravity acts on the young moon, raising slight bulges and slowly draining energy from any earlier mismatch in its spin. The result is a world that now keeps one familiar face toward Earth and one hidden face beyond direct view. The hidden hemisphere is often called the far side. It is not a permanently dark side. Sunlight still reaches it in the regular cycle of the lunar day and lunar night. What remains hidden is not light, but line of sight. From Earth, the moon appears close and well known. Its bright and dark patterns are visible even without a telescope. Generations watch the same rounded form rise, change phase, and set. The dark plains on the near side create shapes that many cultures turn into stories. The brighter rough regions frame those plains with pale and broken texture. This repeated view creates a deep impression of familiarity. Yet the moon's steady orientation hides nearly half of its surface from direct human sight at ground level on Earth. Small effects called librations, slight apparent tilts caused by geometry and orbital variation, allow a little more than half the lunar surface to become visible over time. Even so, the central expanse of the far side remains out of reach from ordinary viewing. For most of human history, that hemisphere exists as a physical reality without an image. The distance between Earth and the moon is great enough to make this hidden region feel remote, yet small enough to keep the moon central in human thought. On average, the moon orbits at about 384,000 kilometers from Earth. That is close in cosmic terms, but still far beyond direct touch. The moon has no substantial atmosphere in the way Earth does. It has only an extremely thin surface-bound exosphere, a sparse envelope of atoms so slight that it does not scatter light like a true sky. Because there is no thick air, the edge between sunlight and darkness on the moon is stark. Dust, rock, slopes, crater rims, and plains stand under raw solar light or sink into black shadow. This clarity matters for observation. Surface forms are not softened by weather, cloud, rain, or flowing water. The moon preserves marks for vast spans of time. Its visible surface becomes a long memory written in stone and dust. The far side shares this airless exposure with the near side. It is made of the same basic lunar materials, shaped by impacts, volcanism, and ancient internal change. Yet before spacecraft, none of that could be seen directly. The existence of a hidden hemisphere creates a scientific tension between closeness and ignorance. The moon is the nearest large world beyond Earth, but half of it remains unseen from the planet below. This fact alone gives the far side a quiet power in science. It is not mysterious because it breaks natural law. It is mysterious because a nearby object, always present in the sky, still withholds a large part of itself from ordinary view. The geometry behind this hidden hemisphere is simple when seen from above. Earth lies near the centre of the Moon's orbit, though the orbit is slightly elliptical rather than perfectly circular. As the Moon travels around Earth, it rotates once in nearly the same amount of time. One full rotation and one full orbit stay linked. The same hemisphere continues to face inward toward Earth. This does not mean the Moon is motionless. It means its turning matches its travelling. A similar effect can be imagined in a much simpler way by thinking of a person walking in a circle while always facing the centre. That person must slowly turn to keep the same side inward. The Moon does the same on a grander scale, governed not by intention but by gravity and time. The far side also has a special place in the larger Earth-Moon system. Earth's gravity dominates the Moon's motion, but the Moon influences Earth as well. It raises ocean tides, slightly affects Earth's rotation, and slowly moves away from Earth over geological time. The Moon's formation itself is strongly linked, in current scientific understanding, to a giant impact early in solar system history. A Mars-sized body is thought to collide with the young Earth, throwing material into orbit that later gathers into the Moon. From that violent origin comes a body that later settles into calm regularity. The far side belongs to this same story. It is not a separate object or a captured shell. It is one hemisphere of a single Moon that forms, heats, differentiates, cools, and records its past across both visible and hidden terrain. Seen from space, the distinction between near side and far side is geometric, not absolute. An astronaut orbiting the Moon passes over both. A spacecraft circling the Moon can image any region beneath it. But from Earth, the division feels profound because communication, observation, and imagination all begin on one side. For early astronomers, the near side becomes a map. They name large dark plains, bright craters, mountain ranges, and ray systems. They chart motions and phases with increasing precision. They measure the Moon's diameter, distance, and changing apparent size. They infer its lack of weather and its heavily cratered nature. Yet the far side remains a blank region in every true sense of direct observation. This absence of data shapes expectation. Some imagine symmetry, assuming the hidden side must resemble the known face. Others remain cautious, aware that hidden terrain can differ for reasons not yet understood. The Moon's phases do not reveal the far side. When the Moon is new, the sunlit half faces away from Earth, but that outward-facing bright half is still mostly part of the near-side hemisphere combined with edge regions. Not a sudden presentation of the far side. The hidden hemisphere stays hidden because visibility depends on orientation, not on illumination alone. This is one of the simplest and most important points in understanding the far side. Darkness is not the issue. Angle is the issue. The far side receives sunrise, noon, sunset, and night, just as the near side does, each lunar day lasting roughly 2 Earth weeks of sunlight followed by roughly 2 Earth weeks of darkness. The hidden hemisphere is illuminated regularly, but for observers on Earth, it turns that illumination away. This geometric separation has practical consequences. Radio communication with the far side is difficult from Earth because the Moon itself blocks direct signals. A lander on the far side cannot simply speak straight home without help. A relay spacecraft is needed in lunar orbit or at a special gravitational balance point. The same blocking effect later becomes scientifically valuable because it shields the far side from much of Earth's radio noise. But here, At the outermost level of the subject, the important fact is more basic. The far side is not just unseen from Earth, it is also physically screened by the moon's bulk. Rock and distance create a true barrier between direct contact and hidden terrain. In this first outer region, the far side is best understood as a condition of orientation. Before mountains, basins, minerals, ice, or deep structure enter the story, there is a simple spatial truth. The moon keeps one hemisphere turned toward Earth and one turned away. The familiar face dominates human memory because it is always available. The far side begins as absence, then as inference, then as a target for instruments. Its scientific value starts with the fact that it is there at all. Close and ordinary in one sense, inaccessible and unseen in another. What NASA and other space agencies later find on their hidden hemisphere gains meaning only because this quiet orbital arrangement first divides the moon into the known and the concealed. For a long time, the far side of the moon exists in science as a hidden surface waiting for light not from the sun, but from a camera. Telescopes on Earth grow larger and sharper, lenses improve, maps of the near side become increasingly detailed. Craters are measured, ridges traced, bright rays followed across the face that looks down toward Earth. Even so, the unseen hemisphere remains beyond reach. No amount of patience at an observatory can change the moon's locked orientation. The problem is not clarity, the problem is angle. To see the far side, an instrument must leave Earth, pass around the moon, and look back across the hemisphere that no human eye has viewed directly before. This movement from ground-based astronomy to spaceflight marks a change in the history of knowledge. It turns a blank region into an observable place. In the middle of the 20th century, that change begins. Robotic spacecraft become the first explorers of the lunar far side. They do not arrive with human footsteps or direct touch. They arrive with radio transmitters, guidance systems, and cameras. Their task at first is simple in concept and difficult in practice. A spacecraft must survive launch from Earth, travel through cislunar space, pass behind the moon, and continue operating while cut off for a time from direct radio contact. Then it must return data once communication is possible again. The first successful far-side images come not from NASA, but from the Soviet Luna 3 mission in the year 1959. This remains one of the great first views in space exploration. The photographs are crude by modern standards, limited in resolution and incomplete in coverage. Yet they carry immense importance. They reveal that the hidden hemisphere is real terrain with its own patterns, not a mirror copy of the near side. What those early images show is immediately striking. The familiar dark lunar plains that dominate much of the near side are far less common. The far side appears brighter overall, rougher, more heavily cratered, and more densely marked by ancient impacts. Its large, dark volcanic plains, called maria, are rare compared with the near side. A maria in this context is a broad plain of dark basalt, a volcanic rock formed from cooled lava, on the near side. Such plains create many of the dark shapes visible from Earth. On the far side, those broad dark areas are scarce and much smaller. Even in the first imperfect images, the contrast is clear enough to change assumptions. The moon is not evenly divided into matching halves. One side shows extensive volcanic resurfacing in wide, dark patches. The other keeps more of its older battered crust exposed. This first glimpse matters not because it offers detail, but because it breaks symmetry. Before spacecraft, it is reasonable to imagine that the unseen side resembles the known one. Nature often produces repeated forms. A roughly spherical moon might be expected to have similar large features on both hemispheres, yet the far side does not present that balance. It carries a different visual character. The first photographs suggest a history shaped by unequal conditions inside the moon, as well as different expressions of ancient impacts and volcanism. At this stage, the reasons remain uncertain. The images simply establish the fact of difference. Science often begins in this way. Observation arrives before explanation. The camera records a pattern, and only later do measurements of composition, gravity, crust thickness, and thermal history begin to explain why that pattern exists. NASA enters this unfolding effort through later lunar missions that improve imaging, mapping, and orbital coverage. During the 1960s, a sequence of American spacecraft adds detail and confidence to what is known. The Lunar Orbiter missions, designed in part to help prepare for Apollo landings, also return extensive photographs of the Moon from orbit. These missions do not focus only on the near side. As they circle the Moon, they gather images from far-side regions as well, helping transform the hidden hemisphere from a rough photographic surprise into a mapped world. Resolution improves, coverage expands. Surface features once seen only as blurred light and dark patches resolve into distinct crater rims, ejecta blankets, overlapping scars, and broken highland terrain. Each new pass adds order to what has been unknown. The far side in these growing image sets appears heavily ancient. Craters lie upon craters. Many are old enough that later impacts cut across them, soften their rims, or partly bury their outlines in debris. The highlands dominate. Highlands in lunar science are the brighter, more elevated, older terrains composed largely of anorthositic crust, a rock rich in light-coloured feldspar minerals. These highlands scatter sunlight strongly and give the far side much of its bright appearance. Even before detailed chemical measurements, the visual difference between dark plains and bright uplands helps scientists separate younger volcanic flooding from older crust. The far side seems to preserve more of that older crust in open view. It looks less resurfaced, less smoothed by vast later lava flows, and more dominated by the accumulated violence of early impacts. The first distant glimpses also alter the emotional tone of lunar science. The near side has long been familiar to human culture. It carries names, myths, and repeated observation across thousands of years. The far side, once revealed in grainy frames, feels at once close and alien. It belongs to the same moon, but it does not present the same face. The difference is not dramatic in a theatrical sense. There are no impossible structures, no sudden signs of biology, no evidence of artificial construction. The surprise is geological. The hidden hemisphere is surprising because it is more ancient-looking, more battered, and less shaped by the wide dark lava seas that mark the side facing Earth. The first real encounter with the far side replaces fantasy with asymmetry. That is a quieter surprise, but in science it is a deeper one. These early images also reveal the limits of visual evidence by itself. A photograph can show brightness, shadow, shape, and relative texture. It can indicate crater density and broad terrain type. It cannot, on its own, fully reveal composition, internal structure, or the reasons why lava floods some basins and not others. It cannot directly measure crustal thickness. It cannot prove how deeply an impact basin excavates the moon's interior. So the first glimpses open questions rather than closing them. Why is the far side so dominated by highlands? Why are the maria so sparse? Why does one hemisphere seem more volcanically resurfaced than the other? Are the causes linked to crust thickness, heat-producing elements, impact timing, or conditions inherited from the Moon's earliest formation. At this point in the historical path, those questions remain waiting. Another important lesson comes from the act of imaging itself. The far side cannot be known through a single dramatic reveal. It becomes known piece by piece, orbit by orbit, transmission by transmission. Early spacecraft produced partial coverage, uncertain angles, and limited resolution. Later missions fill gaps, correct distortions, and refine maps. Science on the Moon grows cumulative. The far side emerges from shadow not in one moment, but through repeated passes by machines that turn hidden terrain into recorded terrain. This slow accumulation suits the Moon. Its surface itself is an archive built over immense time. The scientific picture of that surface grows in a similarly layered way, with each mission adding a new sheet of evidence over the old blank. By the end of these first distant glimpses, the far side is no longer an abstract opposite of the near side. It becomes a hemisphere with a distinct identity grounded in observation. The difference is visible before it is understood. NASA and other space agencies do not find a secret object or a dramatic anomaly. They find a surface that does not match expectation. That mismatch becomes the beginning of a much larger story. The far side, once simply hidden, is now known to be geologically different in broad and important ways. The photographs say this first, quietly and without interpretation. The explanations will come later. For now, the scientific discovery is enough. The Moon has two hemispheres, and when the unseen one is finally observed, it proves to be unlike the face that has looked toward Earth for all of recorded history. With the first images secured and broader mapping underway, the far side of the Moon can now be examined not as a hidden idea, but as a surface with its own overall pattern. At this scale, before attention narrows to single basins, minerals, or deep crust. The most important fact is visual balance across the hemisphere. The far side is dominated by bright, rugged highlands and a dense covering of craters. It lacks most of the broad, dark volcanic plains that make the near side so recognizable from Earth. This difference gives the hidden hemisphere a distinct character. It appears older at the surface, more broken, and less flooded by later lava. The result is not a world of chaos, but a world in which ancient terrain remains more widely exposed. The lunar highlands are the brighter regions of the Moon, elevated in comparison with the lower plains and composed largely of old crust, rich in feldspar-bearing rock. Feldspar is a group of common rock-forming minerals that are often light in colour. On the Moon, this ancient highland crust reflects sunlight strongly. From orbit, it gives the far side much of its pale appearance. These highlands are not smooth plateaus. They are rough, deeply scarred, uneven expanses shaped by impact after impact over immense spans of time. Rims overlap. Small craters crowd the floors and walls of larger ones. Debris from old collisions blankets wide areas. Slopes rise and fall in irregular patterns. In the absence of atmosphere, rainfall, rivers, and active plate tectonics, the marks of this bombardment remain visible for billions of years. Against this bright highland background, the scarcity of Maria stands out. A Maria, in lunar science, is a large plain of dark basalt formed when lava rises and spreads across a basin, later cooling into broad, smooth terrain. Basalt is a volcanic rock formed from molten material that reaches the surface and hardens. On the near side, Maria cover a substantial part of the hemisphere visible from Earth. They are responsible for many of the dark areas long noticed by naked eye observers. On the far side, these basalt plains are far fewer, generally smaller and much less dominant. There are far-side Maria, but they do not define the hemisphere the way near-side Maria do. The broad impression remains one of bright crust, not dark lava seas. This large-scale contrast is one of the Moon's most important geological facts. It is sometimes called the lunar far-side highlands problem, or, more broadly, part of the Moon's global asymmetry. The word asymmetry here means a lack of balance between two halves. The near side and far side are not arranged as mirror images. They carry different proportions of old crust and younger volcanic resurfacing. This does not mean they are made from wholly different origins. Both belong to the same Moon, formed from the same broad early history. But the later expression of that history is not the same on both hemispheres. The far side preserves more of its early exterior. The near side shows more extensive volcanic change. Elevation adds another part of the pattern. Broad topographic measurements from later missions show that the far side highlands tend to stand at greater average elevation than the Maria-dominated lowlands of the near side. Topography means the shape and height of the surface. At this hemispheric level, the Moon is not simply round and even. It contains major differences in height, crustal thickness, and basin depth. The far side presents large tracts of elevated old crust, while the near side includes several lower regions filled by basalt. These differences support what the eye already suggests. The far side is not only brighter and more cratered, it is also more dominated by ancient crust standing in broad, rough relief. The crater density of the far side reinforces the sense of age. In planetary science, crater density is often used as a rough guide to surface age. A surface that has been exposed longer without being renewed tends to accumulate more impacts. A surface that has been resurfaced by lava or other geological activity can erase earlier craters and begin a newer record. The far side's thick population of craters therefore points to widespread preservation of very old terrain. Many regions record the late heavy bombardment and other early phases of solar system impact history. While exact ages depend on detailed dating methods, the broad conclusion is clear. Much of the far side has remained exposed for extraordinarily long spans, retaining scars that later volcanic flooding did not erase. This does not make the far side uniform. Even within a hemisphere dominated by highlands, there is variation in brightness, roughness, crater size, basin overlap, and local volcanic history. Some large impact structures interrupt the general pattern. Some smaller dark plains do occur in basins where lava once rose. Ejecta from large impacts spreads unevenly, creating textured blankets and radial patterns. There are subtle shifts in composition and terrain from one region to another, but the first full regional impression remains stable under closer study. Compared with the near side, the far side is still more rugged, more crater-saturated, and less covered by basalt plains. The absence of extensive Maria has an important visual consequence. On the near side, the large dark plains create strong contrast at a glance. The eye easily separates dark and light regions. On the far side, much of the hemisphere stays within a narrower range of brightness because pale highland materials dominate. This gives the terrain a more uniformly luminous look from orbit, though that apparent uniformity disappears under close inspection. The surface is densely textured. It is filled with crater chains, broken rims, central peaks, and ejecta fields. Instead of large dark shapes, there is a finer grain of geological structure spread across nearly everything. The broad pattern also changes the way sunlight behaves across the terrain. On the Moon, with no thick air to soften illumination, low-angle sunlight casts strong shadows that sharpen the shape of ridges. crater walls, and peaks, on the far side where rough terrain is widespread. Sunrise and sunset conditions reveal countless small relief features. Crater rims catch light while their interiors remain dark. Overlapping depressions create layered patterns of shadow. In this way, the far side becomes especially rich in visible form. Its story is written less in broad, smooth plains and more in accumulated texture. The landscape reads like an exposed crust left open to long impact history. NASA's orbital data, later joined by international missions, confirm this broad description with increasing precision. High-resolution imagery, laser altimetry, gravity mapping, and spectral measurements all support the basic visual truth first seen in early photographs. The far side is the hemisphere of old highlands. The near side is the hemisphere of larger basaltic flooding. This difference does not rest on impression alone. It is measured in composition, elevation, crustal structure, and volcanic distribution. Still, at the scale of this section, it is enough to remain with the visible landscape itself. The Moon's hidden hemisphere is not defined by one isolated discovery. It is defined by a whole surface pattern that becomes clearer the more it is mapped. This pattern is part of what makes the far side surprising in a scientific sense. Many popular expectations look for a single dramatic object or event. The actual surprise is larger and quieter. It lies in the way an entire hemisphere differs from the one facing Earth. The far side is not a secret chamber. It is a different geological face of the same world. That difference begins with landscape. Bright highlands dominate. Dark maria are limited. Craters are abundant. Ancient crust remains exposed across wide regions. These are the broad outer features that define the far side before any move inward to the deeper record preserved within them. At this level, NASA finds a hemisphere whose very surface pattern reveals that the Moon's history is not evenly written from one side to the other. Across the far side of the Moon, the craters do more than cover the surface. They preserve time. Each circular depression, broken rim, central peak, and apron of ejected debris is part of a long record of collision in the early solar system. A crater forms when an asteroid or comet strikes at enormous speed. The force of the impact does not simply dig a hole in the ground. It releases energy so intense that rock is shattered, compressed, melted, and thrown outward in all directions. A crater is therefore not a bowl made by slow pressure. It is the frozen result of an explosion caused by motion. On the far side, where old crust remains widely exposed and later lava flooding is limited, this impact record stays visible with unusual clarity. The Moon is especially good at preserving such records because it has no thick atmosphere, no rain, no rivers, no wind-driven erosion in the terrestrial sense, and no active plate tectonics to recycle its surface. On Earth, most ancient craters are erased, buried, or transformed over time. Oceans, sediment, mountain building, and deep crustal motion remove much of the old evidence. The Moon does not do this on the same scale. Its surface changes slowly. Small impacts continue. Solar radiation and micrometeorites gradually grind rock into finer material called regolith, the loose blanket of dust and broken fragments that covers much of the Moon. Yet large craters remain. Their forms soften over immense spans, but they do not disappear quickly. Because of that, the lunar far side becomes one of the clearest surviving archives of bombardment from the earliest ages of planetary history. Many far-side craters are ancient enough that they overlap in dense layers. One crater cuts across the rim of another. A younger impact lands within the floor of an older basin. Smaller craters pepper the ejecta blankets of larger ones. This pattern is known as crater saturation in its more extreme form, meaning that impacts become so abundant over time that new craters increasingly strike ground already shaped by older impacts. In such terrain, the surface no longer records isolated events in a simple sequence. It records an environment of repeated bombardment. The far side highlands display this condition widely. Their crater density suggests long exposure and limited later resurfacing. In plain terms, much of the far side keeps the scars of very old violence near the surface, almost uninterrupted. The size of these craters ranges widely. Some are tiny pits visible only in high-resolution imagery. Others are immense structures with terraced inner walls, central uplifts, and wide ejector fields. The form of a crater depends partly on size. Small craters tend to be simple bowl-shaped depressions. Larger ones become more complex. Their walls may slump inward in steps called terraces. Their floors may rebound upward after the impact, creating a central peak or peak ring. This rebound happens because the crust behaves briefly like a compressed fluid under extreme shock, then rises as pressure relaxes. On the far side, many complex craters remain sharply expressed. They reveal not only that impact occurred, but how lunar crust responds under sudden colossal force. Some of the most striking far-side craters are those with bright ray systems, though these are less dominant overall than on the near side in the famous case of Tycho. Rays are streaks of brighter material thrown out during an impact and spread across the surrounding surface. They are often more visible when the excavated material is fresher or compositionally different from older weathered soil around it. On the far side, crater rays, overlapping ejecta, and chains of secondary impacts create intricate patterns across the highlands. Secondary impacts are formed not by new asteroids, but by blocks thrown outward from a major collision and landing elsewhere at high speed. These can produce clusters or chains of smaller craters that complicate the landscape. In this way, one large impact can reshape a region far beyond its central cavity. The age of a lunar surface is not read from a single crater alone. It is inferred from crater populations, relationships between overlapping features, and, where possible, radiometric dating of returned samples from related terrains. Radiometric dating is a method that uses the decay of radioactive elements in rocks to estimate age. For the far side, direct sample return is still limited compared with the near side, so scientists rely heavily on crater counting and remote sensing tied to better dated lunar materials elsewhere. Even with these limits, the broad conclusion is secure. The far side preserves some of the oldest large-scale surface units on the Moon, its heavy cratering points back toward the period when the inner solar system experienced frequent major impacts, especially in the first several 100 million years after planetary formation. This is one reason the far side matters beyond lunar science alone. It acts as a surviving witness to a time when Earth, too, was struck repeatedly by large bodies. Earth's own record from that early era is fragmentary, because later geology has erased much of it. The Moon, by contrast, still carries an accessible memory of that shared bombardment environment. The far side is particularly valuable because it has been less altered by widespread volcanic flooding. It preserves old impact history more openly. When NASA maps these craters in detail, it is not only studying lunar scenery, it is also studying conditions that shaped all rocky worlds in the young solar system. The far side's cratered surface also reveals that impact history is not uniform in consequence. Some impacts merely add another scar to old crust. Others excavate deep enough to expose material from below the surface. Some fracture the crust over wide areas. Some create basins so large that they later influence volcanic pathways, thermal evolution, or local gravitational structure. At the scale of this section, however, the craters are still best seen as a distributed record rather than as singular special cases. They cover the terrain so densely that the surface itself becomes a time-stamped field of impact outcomes. The far side does not hide this past. It displays it nearly everywhere. There is also an important visual truth in the crater record. A heavily cratered world appears still. Nothing moves across the far side in the way clouds move over Earth or dunes migrate across Mars. Yet this apparent stillness is deceptive. Each crater is the mark of extreme motion from the past. The surface is static now, but it is shaped by ancient velocity. Objects once strike from many directions, at many sizes, over immense spans of time. The quiet landscape is built from collisions. The older the terrain, the more of those collisions it keeps. On the far side, old age and preserved roughness come together so completely that the landscape feels almost entirely impact-made, even though the crust beneath it has its own deeper history. NASA's detailed orbital work strengthens this reading. High-resolution cameras trace rim degradation, overlap sequences, ejecta textures, and small crater populations. Laser measurements show depth and relief. Spectral data reveal excavated material in and around some crater floors and peaks. Gravity mapping helps distinguish buried basin structures from simple surface impressions. Together, these tools confirm what the eye first suspects. The far side is not merely spotted with impacts. It is a hemisphere whose visible exterior is deeply governed by impact accumulation over geological time. The craters are not decoration. They are structure, chronology, and evidence. What NASA finds on the Moon's far side in this region is therefore neither a hidden artifact nor a sudden anomaly. It is a profound continuity of scars. The far side preserves a near-planet-wide impact record in terrain that later processes have only partly modified. It shows how ancient crust can remain exposed when volcanic resurfacing is limited. It shows how the Moon serves as an archive of early solar system violence. Most of all, it shows that surprise in planetary science often comes not from one impossible object, but from the sheer persistence of evidence. On the far side, crater after crater holds that evidence in place, turning rock and dust into a visible memory of deep time. Among all the structures on the Moon's far side, one stands apart in scale, depth, and scientific importance. This is the South Pole-Aitken basin, one of the largest known impact basins in the solar system. A basin is a very large impact structure, wider and deeper than an ordinary crater and often reshaped by later events across immense spans of time. The South Pole-Aitken basin stretches across a vast part of the lunar far side, reaching from the southern polar region toward lower latitudes on the hidden hemisphere. Its diameter is about 2,500 kilometers. Its depth, measured relative to surrounding highlands, is several kilometers. These numbers alone place it among the grandest scars on any rocky world that humans have studied closely. Yet its importance lies not only in its size. It matters because such a colossal impact may open a window into deeper parts of the Moon than would otherwise be visible. At the broad surface level, the basin does not always look like a single simple ring in the way a smaller crater might. Time has modified it. Later impacts strike across it. Ejecta from other collisions lies over parts of it. Volcanic materials appear in some sectors. The basin's boundary is therefore not always obvious to the eye in a single photograph. Its identity emerges through mapping, elevation data, gravity measurements, and the overall arrangement of terrain. When these are combined, the structure becomes clear. The far side contains a huge depressed region, ancient and complex, with a distinct geological character that separates it from surrounding highlands. This is the South Pole-Aitken basin, often shortened to SPA in scientific discussion, though its full name carries more weight in calm description. It is a feature so large that it helps organise the geology of much of the far side around it. The age of this basin places it very early in lunar history. It likely forms more than 4 billion years ago, during an era when large impacts are far more common than they are now. This early timing matters because the event occurs while the Moon is still young in geological terms, with internal heat, layered crust, and a surface not yet shaped into its later pattern. A collision large enough to create the South Pole-Aitken basin releases extraordinary energy. The impactor, probably tens or even more than 100 kilometers across, strikes at immense speed. In moments, crust is shattered, compressed, heated, and excavated on a scale almost beyond ordinary comparison. Rock behaves briefly like fluid under shock. Material is thrown outward across huge distances. The basin floor is left lower than surrounding terrain. The crust beneath it may be thinned. Deep material may be brought closer to the surface or exposed directly in places. This possibility of exposing deeper lunar layers is one reason the basin holds such scientific value. Most of the Moon's surface shows the outer crust. Even large ordinary craters excavate only a limited depth. But a basin of this scale may cut far enough to sample rocks from the lower crust, and perhaps material influenced by the upper mantle. The mantle is the thick layer beneath the crust. On the Moon, as on Earth, it is composed of denser rock lying below the outer shell. Direct access to lunar mantle material is extremely difficult. Scientists therefore look for places where giant impacts may have brought deeper material upward. The South Pole-Aitken basin is one of the best candidates for such a natural excavation. This does not mean the mantle lies openly uncovered across the whole basin floor. That remains uncertain. Observations indicate unusual compositions in some parts of the basin, but exactly how much material comes from lower crust or upper mantle is still actively studied. The basin also helps explain why the far side cannot be understood as a simple field of ordinary craters alone. It is not just another impact among many. It is a foundational event in the far side's geological history. Later craters form inside it. Some volcanic deposits appear within or around parts of it. Tectonic and thermal consequences may follow from the crustal disturbance it creates. Tectonic in this sense refers to deformation of the crust, such as faulting, uplift, or structural adjustment after stress. A basin this large changes the conditions of the region it occupies. It alters topography, crustal thickness, and possibly the pathways along which later melts can move. Even when its original form is partly obscured by time, its influence remains. The South Pole-Aitken basin is also notable for the contrast between its immense scale and its restrained visual impression. It is not a sharply defined hole with a single crisp rim visible from every angle. Instead, it is a giant ancient depression whose meaning emerges through patient measurement. This makes it scientifically rich. The Moon often preserves history in plain sight, but not always in simple shapes. In the case of this basin, the larger structure on the far side must be reconstructed through multiple kinds of evidence. Elevation maps show the broad low region. Gravity data reveal differences in mass distribution beneath the surface. Spectral observations, which measure reflected light at different wavelengths, help identify minerals and compositions that differ from surrounding terrain. Together, these methods allow NASA and other investigators to study a feature whose true scale exceeds what ordinary vision alone easily grasps. Some parts of the basin contain dark basaltic deposits, though not on the same broad scale as Nearside Maria. These localized volcanic plains are important because they suggest that, in some areas, magma reaches the surface after the basin-forming event. Magma is molten rock below the surface. When it erupts and cools, it forms basalt. The presence of basalt in parts of the basin indicates that the impact may contribute to later volcanic activity by thinning crust or changing subsurface conditions. Still, the basin remains primarily an impact structure, not a volcanic province. Its identity comes from collision first, with later volcanism as a secondary chapter written within the scar. NASA's orbital missions add greatly to understanding this enormous feature. The Lunar Reconnaissance Orbiter provides detailed topography and imaging. The Gravity Recovery and Interior Laboratory mission maps variations in the Moon's gravity field with high precision, helping scientists infer hidden structure beneath the basin. These observations show that the South Pole-Aitken basin is not only broad and deep, but also tied to density anomalies below the surface. Some studies suggest unusually dense material beneath parts of the basin, perhaps linked to mantle uplift, impact melt, or concentrations of metal-rich residues from the ancient collision. The exact explanation remains uncertain, but the evidence confirms that the basin is not a superficial mark. It is a major wound in the Moon's crust with deep structural consequences. What NASA finds here is therefore one of the far side's greatest scientific surprises. The hidden hemisphere contains not merely more craters, but one of the most important impact basins known anywhere nearby in the solar system. It is ancient, immense, and potentially revealing of deep lunar structure. It shows that the far side is not simply the less volcanic half of the Moon. It is also home to a giant natural excavation, a place where early catastrophe may have brought buried history closer to view. In the calm geography of the far side, the South Pole-Aitken basin stands as a vast inward step, where surface pattern begins to give way to the deeper architecture of the Moon itself. Around the great impact basins of the lunar far side, the crust does not remain as a simple broken shell. It rises, collapses, tilts, fractures, and settles into new forms. The outer crust of the Moon records these changes in mountain rings, uplifted rims, faulted slopes, and wide belts of shattered ground. On the far side, where old terrain remains broadly exposed, these structural effects are preserved with unusual clarity. The surface is not only marked by pits made from collision, it is also built from crust that responds to collision by bending and breaking. In this region of the story, the far side becomes a place where the outer shell of the Moon shows how immense impacts reshape more than the point of contact. When a very large body strikes the Moon, the event does not end with excavation. The crust around the impact site is subjected to sudden stress far beyond ordinary rock strength. At the moment of collision, shock waves travel outward and downward. Rock is compressed, heated, and displaced. Then, as the pressure falls, parts of the surface rebound upward while other parts slump inward. The result is a structure far more complex than a simple depression. Large craters and basins often develop raised rims, terraced inner walls, central uplifts, and outer rings of disturbed material. In the far side highlands, these features accumulate across great stretches of terrain. Their preservation allows scientists to read how the Moon's crust absorbs and responds to catastrophic force. The mountain rings around giant basins are among the most impressive of these structures. They are not mountains formed by plate collision, as many mountain chains on Earth are. The Moon has no active plate tectonics like Earth's. Instead, these rings are produced when crust is thrown up, displaced, and reorganized during impact. In some cases, several concentric rings can form, marking zones where the crust responds differently at different distances from the center of the event. These ring structures may be incomplete, degraded, or buried in part by later impacts and ejecta, but their broad patterns remain visible in topography. They show that the Moon's crust behaves in a layered and dynamic way under shock. It does not merely crack at one point, it deforms across entire regions. Raised rims are one of the simplest expressions of this process. Around a crater or basin, the edge stands above the surrounding terrain because excavated material is forced outward and upward during the impact. Yet the rim is rarely a perfect circle once time has acted on it. Later impacts break it, segments collapse, debris softens its profile. On the far side, many rims survive in partial form, creating arcs of mountains, discontinuous ridges, and broken high ground. These fragments are important because they preserve the original geometry of a large impact even when the crater itself has been altered. A degraded rim is still evidence of past uplift. It marks where the crust once rose under pressure and remained high after the energy of collision passed. Inside many large impact structures, the walls do not stay steep and clean, they slump. This slumping creates terraces, broad step-like ledges where crust has collapsed inward under gravity after the initial excavation. Such terraced walls show that lunar rock, though rigid over long spans, can move abruptly when destabilized. The crust behaves partly like brittle stone, and partly like a material that can flow or fail under extreme shock and steep slopes. On the far side, terraced inner walls and collapsed sectors appear in many large craters. They reveal the mechanical limits of the crust. Even without water or air, gravity is enough to pull over-steepened slopes downward once an impact has torn the ground open. Faults add another layer to this damaged landscape. A fault is a fracture in rock along which movement has occurred. On the Moon, large impacts can generate systems of faults both within and beyond crater walls. Some are normal faults, where one block drops relative to another as the crust stretches or collapses. Others may reflect compression or rebound. On the far side, faulted scarps, linear breaks, and offset blocks help map how stress spreads through the outer shell after giant impacts. These structures are not always easy to see in ordinary photographs, but topographic data and high-resolution imaging reveal them more clearly. They show that the crust is not only shattered at the center of a blow, it is reorganized across wide belts of terrain. The South Pole-Aitken basin provides one of the clearest large-scale examples of this broken crust geography. Its vast depressed interior, uneven rings, and surrounding uplift reflect a collision powerful enough to reshape the far side outer shell on a hemispheric scale. Even where its original ring structure is hard to trace in one continuous outline, the surrounding topography still carries the mark of that event. The crust is thinner there than in many neighbouring regions. The floor lies lower. The structural pattern suggests excavation, rebound, and long-term adjustment after impact. Other large far-side basins and craters repeat these themes at smaller scales. Again and again, the hidden hemisphere shows that collision leaves behind architecture as well as scars. This broken architecture affects later lunar history. Fractured crust is not the same as intact crust. Cracks and zones of weakness may influence how heat moves, how stress is released, and whether molten material from below can approach the surface. On the far side, where widespread maria are limited, these effects do not produce the same broad basalt flooding seen on the near side. Still, local volcanic deposits in some impact structures suggest that crustal damage can help create pathways for magma. Magma in this sense is molten rock beneath the surface. If the crust is thinned or fractured enough, Some of that melt may rise. The effect is not universal, and on the far side it remains comparatively restricted. But the principle matters. Giant impacts do not simply destroy terrain. They can also set conditions for what happens later. This shattered crust also controls the appearance of the landscape at smaller scales. Broken rims produce shadowed ridges, slumped walls create uneven benches and scarps, faulted blocks disturb what might otherwise be smooth crater floors. Debris from uplifted highlands spreads outward in irregular aprons, under low-angle sunlight. These features give the far side a strongly textured surface. The eye sees not only circles, but folds of relief within and around them. The moon's lack of atmosphere makes these forms especially sharp. Light falls directly on ridge crests, while deeper fractures remain dark. In this way, the far side's broken crust becomes visually legible. One can often see, even before detailed analysis, that the ground has not merely been struck, it has been rearranged. NASA's orbital instruments make this rearrangement measurable. Laser altimeters record height differences across rims, terraces, and basin floors. Cameras resolve slope failure, block fields, and fracture patterns. Gravity measurements reveal buried basin structure and changes in crustal thickness beneath old impact zones. These tools confirm that the far side's mountain rings and broken terrains are not accidental local oddities. They are systematic results of repeated large impacts acting on an ancient crust. The outer shell of the moon has been deformed in layers. Some structures are still bold, others survive as subdued patterns beneath later damage. Together they form a map of crustal response. What NASA finds in this region of the far side is therefore a record of structural violence preserved in stone. The hidden hemisphere does not only show where impacts happen, it shows how the moon's outer shell rises, collapses, and fractures when those impacts are immense. Mountain rings, uplifted rims, terraced walls, and broken crust all belong to the same process. They reveal a world whose surface is not passively scarred, but actively reshaped by force. In the far side highlands, those reshaped forms remain exposed across wide distances, allowing the outer crust itself to speak in ridges, faults, and shattered relief. Beneath the cratered highlands and broken rims of the lunar far side lies one of the most important internal differences on the moon. The crust there is, on average, thicker than the crust on much of the near side. The crust is the moon's outer rocky shell, the solid layer that forms the surface and extends downward before giving way to deeper interior material. This difference in thickness is not a small local detail. It is one of the main reasons the two hemispheres look so unlike each other. The far side is not only brighter and more heavily cratered at the surface, it is also built on a thicker outer shell. NASA's orbital measurements help make this clear, turning what first appears to be a visual contrast into a deeper structural fact. Early photographs suggest that the far side preserves more ancient highland crust, but photographs alone cannot measure thickness. That requires another kind of investigation. Scientists study the moon's gravity field, topography, and the way mass is distributed beneath visible landforms. Gravity varies slightly from place to place depending on how much material lies below the surface and how dense that material is. A spacecraft moving over the moon responds to these variations in tiny but measurable ways. By tracking those motions with great precision, researchers can infer hidden structure below the visible terrain. Combined with height measurements and models of lunar composition, these data show that the crust is not uniform across the moon. The far side generally carries a thicker crust than the near side. This difference helps explain the far side's elevated, highland-rich appearance. A thicker crust means a larger volume of relatively light outer rock standing above deeper interior material. Much of the lunar crust is made of ancient anorthositic rock, rich in feldspar minerals that are less dense than the rocks below. In the Moon's early history, when much of the outer body may have been molten or partly molten, these lighter minerals are thought to float upward and form a primordial crust. The idea of a lunar magma ocean is widely used to describe this stage. A magma ocean is a deep layer of molten rock early in a world's history. As it cools, different minerals separate by density. Lighter material rises and crystallizes into crust, while denser material remains below. If that early crust does not form or remain evenly everywhere, long-term differences between hemispheres can emerge. On the far side, the crust appears to be substantially thicker than on the near side, though the exact amount varies by location and by the model used. The broad conclusion remains stable. This is not a surface illusion caused only by different lighting or crater density. It is a structural asymmetry that extends downward, in some regions of the far side. The crust may be tens of kilometers thicker than comparable regions on the near side. Such a difference is large in lunar terms. It affects how impacts excavate the ground, how easily magma can rise, how topography is supported, and how the Moon's thermal history plays out over time. The question then becomes how this uneven crust comes to exist. Observations support the asymmetry, but the exact origin is still studied. Several ideas have been proposed within mainstream lunar science. One possibility is that early heat from Earth affects the near side of the young Moon when the Moon is still forming and much closer to Earth than it is now. If the near side remains warmer for longer, cooling and crystallization patterns may differ across the two hemispheres. In that case, more of the light crust-forming minerals could concentrate on the far side, building a thicker shell there. Another possibility involves the uneven distribution of heat-producing elements, and later, internal evolution. It is also possible that large impacts and prolonged magma movement helps strengthen the difference after it begins. Observations indicate a real crustal asymmetry. It remains uncertain exactly how much each early process contributes to creating it. Whatever the origin, the consequences are clear in the far side landscape. A thicker crust is harder for magma to penetrate. Molten rock rising from depth must travel farther to reach the surface. It must also force its way through a stronger, thicker barrier. If the path is too long or the pressure too low, the magma may stall, cool, or spread below ground instead of erupting. This is one major reason the far side shows fewer maria. The broad, dark basalt plains that flood many near-side basins are much less common on the hidden hemisphere because the outer shell there is less easily breached. At this stage of the story, it is enough to note the structural condition itself. The far side's crust is thicker, and that thickness shapes what the surface can and cannot become. The thicker crust also affects impacts. When an asteroid or comet strikes the far side, the impact excavates through more highland material before approaching deeper layers. This helps preserve the bright anorthositic character of the surface across wide regions. It also influences the form of basins and the kinds of materials exposed in crater walls, central peaks, and ejecta blankets. A giant basin such as South Pole-Aitken is especially important because it cuts through this thick crust and may reach unusually deep material. In this sense, the far side's thicker outer shell makes large excavations scientifically valuable. They serve as rare windows into what lies beneath an otherwise substantial lid of ancient crust. Topography and crustal thickness are closely linked as well. The far side's highlands stand higher in broad regional terms partly because of this thick crustal foundation. The Moon's surface is not supported in exactly the same way as Earth's continents, but the general principle still holds that lighter crust can stand at higher levels relative to denser material below. The far side, rich in old highland crust, reflects this pattern. It is not merely rough because it is ancient. It is structurally elevated in many areas because of the character and thickness of its outer shell. NASA's gravity and topographic measurements help reveal this relationship, showing that the visible terrain is tied to deeper mass distribution. There is also a quiet elegance in the way this crustal difference explains several separate observations at once. The far side is brighter because ancient feldspar-rich highland crust dominates its surface. It is more heavily cratered because those highlands remain exposed and less covered by later lava. It has fewer large maria because the thick crust makes widespread volcanic flooding more difficult. It stands differently in elevation because its outer shell is not the same as the near sides. What first appears as a set of disconnected features begins to resolve into one integrated structure. The Moon's two hemispheres are not only different in appearance, they are different in architecture. NASA's more recent missions help transform this idea from inference into measured reality. Detailed topographic mapping and refined gravity analysis provide stronger estimates of crustal thickness than earlier generations of lunar science can achieve. These results do not remove every uncertainty. The Moon still keeps some of its earliest internal history beyond complete recovery. Yet the main picture is firm. The far side is the hemisphere of thicker crust. This is one of the deepest truths yet found beneath its old bright terrain. What NASA finds here is a hidden asymmetry beneath the visible one. The surprise of the far side is not only written across its cratered surface, it is built into the depth of the Moon's outer shell. A thicker crust supports the old highlands, limits eruption, preserves ancient terrain, and helps make the hidden hemisphere what it is. In this region, the far side ceases to be only a landscape of scars and becomes a structural half of the Moon with its own weight, thickness, and long geological consequence. With the far side's thicker crust now in view, one surface fact begins to make deeper sense. The hidden hemisphere contains far fewer maria than the near side. The maria are the dark volcanic plains that spread across many large basins on the hemisphere facing Earth. They form when magma rises from below, erupts onto the surface, and cools into basalt. Basalt is a dark volcanic rock made from once molten material on the near side. This process covers wide low regions and creates many of the broad dark shapes visible from Earth without a telescope. On the far side, by contrast, these plains are scarce, smaller, and more scattered. Their absence is not total, but it is striking. The question is no longer whether this difference exists. The question is why so much less lava reaches and floods the far side surface. At first glance, a large impact basin might seem equally likely to fill with basalt wherever it forms. An enormous collision digs out a low region. That depression could then act as a container for later lava. On the near side, many maria do indeed occupy large impact basins, but an empty basin is not enough. Lava must still be generated below, remain molten long enough to move, and find a path upward through the crust. This means that maria depend on both impact history and internal conditions. A basin can be available at the surface while the deeper plumbing fails to deliver enough magma. On the far side, this appears to be the common outcome. Many impact scars remain as cratered or broken highland terrain rather than becoming broad basalt plains. The thickness of the crust is one of the main reasons. A thicker crust is a stronger and longer barrier between deep melt and the surface. Magma rising from the lunar interior must move upward through fractures, weak zones, or pathways created by stress and pressure. If the crust is thin enough, and if the melt is abundant enough, eruptions become more likely. If the crust is thick, magma may stall before reaching the top. It can cool underground, spread sideways, or freeze in place within the crust. On the far side, where the crust is generally thicker, this obstacle is greater. This does not prevent all volcanism, but it reduces the likelihood of the enormous basalt floods that create the largest maria. The result is a hemisphere where ancient bright crust remains dominant. Heat is the other major part of the story. Basaltic eruptions require not only a route to the surface, but sufficient internal heat to generate and sustain melt. The Moon was much hotter in its early history than it is now. Over time, it loses heat and volcanic activity declines. The timing and location of volcanic eruptions therefore depend on where heat remains concentrated and how easily that heat can produce melt in the mantle or lower crust. Observations show that the near side contains a stronger concentration of certain heat-producing elements than the far side. These elements, through radioactive decay, help keep parts of the interior warmer over long spans. A warmer interior makes melting more likely. This uneven heat distribution is one reason volcanic flooding becomes much more extensive on the near side. On the far side, lower concentrations of these heat-producing materials, combined with thicker crust, create a difficult environment for large-scale mare volcanism. Even where impact basins exist, the ingredients do not come together as often in the same favourable way. There may be insufficient melt, insufficient pressure, insufficient crustal thinning, or all three. Some far-side basins do contain patches of basalt, showing that volcanism is not absent. But those patches usually remain limited compared with the giant maria of the near side. In scientific terms, the far side experiences less extensive volcanic resurfacing. In plain terms, the hidden hemisphere keeps more of its original battered skin because less molten rock rises to cover it. The shape of the basins also matters. A large impact can thin the crust locally, creating a region where magma later finds a somewhat easier route upward. This helps explain why the maria that do exist on the far side often occupy specific basins or low areas. The South Pole-Aitken basin, for example, includes localized volcanic deposits. These suggest that the giant impact there changes subsurface conditions enough to allow some magma to reach the surface. But even in such a major basin, the flooding is limited compared with what happens in many near-side basins. This difference shows that basin formation alone does not determine the outcome. Crustal thickness and internal heat still constrain how much lava can emerge. The far side's lack of broad maria has major consequences for what is visible today. Without large basalt floods, older impact craters remain exposed. Highland materials continue to dominate brightness. Surface ages appear older because fewer later lavas erase earlier scars. The crater record stays more complete. In this way, the absence of maria becomes a form of preservation. What the far side lacks in volcanic plains, it gains in the survival of ancient crustal history. The hemisphere remains more like an open archive from the Moon's early age, while the near side has been rewritten more heavily by later eruptions. There is also a compositional contrast tied to this difference. Basalt is darker and denser than the anorthositic highland crust. Where basalt floods a basin, the visual appearance of the surface changes strongly. Dark plains replace bright rough terrain. On the far side, because such flooding is limited, the bright feldspar-rich crust remains the dominant expression of the landscape. This is why the hidden hemisphere looks so different in global images. The contrast is not just about crater density, it is about what material is left exposed at the surface. The near side displays more volcanic rock. The far side displays more primordial crust. NASA's orbital measurements help confirm these relationships. Spectral data identify mineral signatures associated with basalt and distinguish them from highland rock. Topographic data show where basins and low plains occur. Gravity studies help estimate crustal thickness and local structure beneath volcanic areas. Together, these observations reveal a coherent picture. Basaltic plains on the far side do exist, but they are more restricted because the conditions that favor widespread eruption are less common. The Moon's volcanic history is therefore uneven across its two hemispheres. One side is more open to flood volcanism, the other resists it. Uncertainty remains in the details. Scientists continue to refine models of melt generation, crustal evolution, and the distribution of heat-producing materials. It remains uncertain exactly how much of the far side's volcanic scarcity is caused by primordial crustal differences, how much by later thermal evolution, and how much by the location and timing of giant impacts. But the main conclusion is well supported. The far side has fewer maria because it is less favourable ground for large basalt floods. Its crust is thicker, its internal heat budget differs, and its pathways to the surface are more limited. What NASA finds in this region of the Moon is therefore an absence with deep meaning. The surprise is not that the far side has no maria at all. The surprise is that such a nearby hemisphere has so few of them compared with the side facing Earth, and that this scarcity reveals an entire chain of structural and thermal differences within the Moon. The missing dark plains are not empty spaces in the story. They are evidence. They show where magma does not rise easily, where heat is less concentrated, and where the old bright crust remains in command of the surface. On the far side, what is missing becomes one of the clearest signs of how differently the Moon's two hemispheres have evolved. Beneath the visible differences in terrain and crustal thickness lies a more subtle contrast in the Moon's internal composition. Certain elements within the Moon produce heat as they decay over time. These are called heat-producing elements, and they include potassium, rare earth elements, and phosphorus. In lunar science, this combination is often referred to as creep, a name formed from the first letters of those components. Creep is not a separate mineral in itself, but a geochemical signature, a way of describing material enriched in these particular elements. This enrichment matters because it affects how much heat remains within parts of the Moon's interior over long spans of time. Observations show that creep-rich material is not evenly distributed across the Moon. It is concentrated much more strongly on the near side, especially in a region associated with large volcanic plains and deep basins. This near-side concentration is sometimes called the Procellarum creep terrain, a broad area where heat-producing elements are more abundant. The far side, by contrast, contains much less of this enriched material. This uneven distribution adds another layer to the Moon's asymmetry. It is not only the crust that differs in thickness. The internal chemistry also varies from one hemisphere to the other. The presence of creep influences the thermal history of the Moon. As radioactive elements decay, they release heat slowly over time. This heat can help maintain higher temperatures in surrounding rock, making it easier for melting to occur in the mantle or lower crust. Where creep is concentrated, the local interior can remain warmer for longer periods. This supports the generation of magma and increases the likelihood that volcanic activity will occur. On the near side, where creep is more abundant, this added heat aligns with the presence of thinner crust. Together, these conditions favour the extensive basalt flooding that forms large maria. On the far side, the relative absence of creep reduces this effect. With fewer heat-producing elements, the interior cools more efficiently. Lower temperatures make melting less common or less sustained. Even when some melt forms, the thicker crust creates an additional barrier to eruption. In this way, the chemical asymmetry reinforces the structural asymmetry. The far side becomes a region where both heat supply and access to the surface are limited. This helps explain why large-scale volcanic resurfacing is rare there compared with the near side. The origin of this uneven distribution of creep remains an area of active study. One widely discussed idea connects it to the Moon's early magma ocean. As the Moon forms and cools, lighter minerals rise to form the crust, while heavier minerals sink. Some elements that do not fit easily into the crystal structures of the main minerals become concentrated in the remaining liquid. This residual melt, enriched in potassium, rare earth elements, and phosphorus, may collect in specific regions rather than spreading evenly. Over time, this enriched material becomes trapped in certain parts of the Moon's interior. If the distribution is uneven from the beginning, later geological evolution can amplify that difference. Another idea considers the role of Earth in the Moon's early development. When the Moon forms, it orbits much closer to Earth than it does today. Earth's heat and gravitational influence could affect how the Moon cools. If the near side remains warmer for longer, it may delay crystallization in that region, allowing creep-rich material to accumulate there. The far side, facing away from Earth, may cool more quickly, forming thicker crust and trapping fewer heat-producing elements near the surface. Observations indicate a strong near-side concentration of creep, but the exact processes that produce this pattern remain uncertain in detail. The consequences of this chemical difference extend beyond volcanism. Heat distribution influences how the Moon's interior evolves over time. Regions with more heat may experience more prolonged internal activity, including slow movement of material, partial melting, and localized tectonic adjustments. Regions with less heat cool and stabilize more quickly. The far side, with its lower creep abundance, tends toward earlier cooling and longer preservation of its ancient crust. This aligns with the heavily cratered, highland-dominated surface seen today. Creep also leaves a detectable signature in remote sensing data. Instruments that measure the energy emitted or reflected from the lunar surface can identify variations in composition. Gamma-ray spectrometers and other sensors can detect the presence of specific elements, helping map where creep-rich material is concentrated. These measurements confirm that the near side carries higher levels of these heat-producing elements, while the far side remains comparatively depleted. This evidence supports the broader interpretation that chemical and thermal asymmetry plays a central role in shaping the Moon's two hemispheres. In the context of the far side, the importance of creep is not that it is entirely absent, but that it is less abundant. Even a reduced presence can contribute to localized melting and limited volcanic activity. This helps explain why small patches of basalt appear in some far-side basins. These areas may represent places where conditions briefly align to allow magma to reach the surface. However, without a strong and widespread concentration of heat-producing elements, such events remain limited in scale. The combination of crustal thickness, impact history, and chemical distribution forms a coherent picture. The far side is not simply a quieter version of the near side. It is a region where multiple factors converge to limit volcanic resurfacing and preserve ancient terrain. The lack of extensive creep enrichment reduces internal heating. The thicker crust restricts magma movement. The result is a hemisphere that retains more of its early geological record. NASA's findings in this region of lunar science highlight how composition and heat are as important as visible terrain. The far side's appearance cannot be fully understood by looking only at craters and basins. It requires an understanding of what lies within the moon, how heat flows, and how elements are distributed. The surprise is not a single discovery, but the realization that the moon's internal chemistry is uneven in a way that shapes its entire surface expression. In this deeper layer of the story, the far side reveals itself as a hemisphere defined by what it lacks as much as by what it contains. It lacks the strong concentration of heat-producing elements found on the near side. It lacks the conditions needed for widespread volcanic flooding. These absences are not empty gaps. They are structural truths that guide the moon's evolution. Through them, the far side becomes a quieter but more enduring record of the moon's early state, shaped by chemistry as much as by impact and structure. The far side of the moon offers fewer returned samples than the near side, yet it is not beyond material study. Scientists learn about its composition through a careful combination of lunar meteorites, orbital spectroscopy, crater excavation, and comparison with rocks collected elsewhere on the moon. A meteorite in this context is a fragment of rock that travels from one world to another and survives passage to the ground. Some meteorites found on Earth are identified as pieces of the moon, thrown off the lunar surface long ago by large impacts. Most cannot be tied to an exact place of origin, yet together they widen the range of known lunar material. They help reveal what kinds of crust and volcanic rock exist beyond the specific landing sites of the Apollo missions, most of which sample the near side. This indirect route matters greatly for the far side because direct sampling there remains limited. The near side benefits from the Apollo landings, which return rocks and soil from selected sites. Those samples transform lunar science by allowing laboratory analysis of age, chemistry, mineral content, and isotopic history. The far side does not yet enjoy such abundant physical return. As a result, its material character must be reconstructed through remote measurements and natural fragments delivered by impact. This does not make the science weak. It makes it more comparative, more inferential, and more dependent on the relationship between surface expression and measurable composition. One of the clearest broad conclusions is that the far side is dominated by anorthositic highland material. Anorthosite is a light-coloured igneous rock rich in feldspar, especially plagioclase feldspar. Igneous rock means rock that forms from molten material that cools and solidifies. On the moon, anorthosite is closely associated with the primordial crust, the early outer shell that crystallizes from the lunar magma ocean. Because the far side preserves more of its ancient crust and experiences less broad basalt flooding, this highland composition remains widely exposed. Orbital measurements of reflected light support this interpretation. Different minerals reflect and absorb light differently across wavelengths, allowing spacecraft instruments to infer surface composition from orbit. The far side consistently shows the signatures expected from feldspar-rich crust over large areas. Spectroscopy is central to this work. Spectroscopy is the study of how matter interacts with light at different wavelengths. On the moon, instruments record reflected sunlight from the surface and examine which wavelengths are absorbed or reflected more strongly. Certain minerals, such as pyroxene, olivine, and feldspar-rich materials, produce recognizable patterns. Basaltic regions tend to show stronger signatures of iron-bearing minerals such as pyroxene, while highland crust often reflects a different pattern, associated with feldspar dominance and lower iron content. Through this method, NASA and other missions build compositional maps of the moon without touching the ground. These maps confirm that the far side is generally less iron-rich at the surface than many basaltic near-side maria and more representative of the old feldspathic crust. Lunar meteorites add an important counterpoint. These rocks arrive on Earth after impacts blast them off the Moon, send them through space, and eventually drop them onto Earth's surface, because they are random ejecta rather than planned samples. They may come from regions not visited by human missions. Some lunar meteorites contain hyaline material consistent with ancient Northersitic crust. Others contain basaltic or mixed compositions, showing that volcanic rocks exist across the Moon beyond the major near-side maria. Their ages and chemistry suggest a Moon more diverse than the Apollo collection alone might imply. Still, the meteorite record supports the overall picture rather than overturning it. The far side remains crust-dominated, and its basaltic contributions appear more limited. Large craters and basins help expose deeper material that remote sensing can then detect. When an impact digs into the crust, it throws buried rock onto the surface and lifts some material into central peaks or ring structures. These exposed rocks provide natural drill sites without drilling. By studying the composition of crater walls, central uplifts, and ejecta blankets, scientists infer what lies below the weathered surface soil, on the far side. This is especially useful because thick regolith and ancient terrain can otherwise mask deeper layers. A central peak rich in unusual minerals may indicate excavation from lower crustal depths. A dark patch within a basin may reveal basaltic fill. A chemically distinct ejecta blanket may mark buried variations in the crust. In this way, impacts do not only scar the far side, they also reveal it. The far side's relative lack of broad basalt plains means its compositional story is less dominated by volcanic resurfacing and more by preserved crustal materials. This helps explain why remote sensing there often emphasizes the ancient outer shell of the Moon. Yet the story is not chemically simple. There are local variations. Some basins contain basaltic deposits. Some excavated materials suggest lower crustal rocks, different from the surface highlands. Some regions in and around giant impact structures show mineral assemblages that may indicate deeper origins or unusual impact melting. The Moon's far side is not compositionally uniform. It is merely more strongly governed by old crust than the near side is. NASA's data contributes substantially to this picture through several missions. Clementine in the 1990s provides global multispectral imaging, helping distinguish broad compositional units across the Moon. Lunar Prospector maps elemental abundances, including key indicators of geochemical variation. The Lunar Reconnaissance Orbiter adds higher resolution imaging and topographic context. Other international missions further strengthen mineral maps and refine interpretations. Together, these records allow scientists to compare bright highlands, dark volcanic units, basin interiors, crater ejecta, and polar terrains with increasing precision. The far side emerges not as a blank highland sheet, but as a structured field of compositional clues. One of the most important insights from this material evidence is that the Moon's visible asymmetry has a real chemical foundation. The far side is not merely brighter because of lighting or roughness. It is brighter because feldspar-rich crust remains dominant over wide regions. The near side is not merely darker because it has flatter terrain. It is darker because basaltic volcanic rock covers large plains. These are material differences. They can be measured, mapped, and tested against meteorites and returned samples. The Moon's two hemispheres are therefore not only morphologically distinct, they are compositionally distinct at the surface, in ways that match their different geological histories. Uncertainty remains, especially where remote sensing cannot fully separate mixed materials, or where meteorites cannot be assigned to exact source regions. It remains uncertain how representative some lunar meteorites are of the far side specifically, and some interpretations of deep excavated material are still debated. Even so, the consensus picture is clear. The far side is a crust-rich hemisphere with limited basaltic flooding, an important local compositional diversity tied to impacts and ancient structure. What NASA finds here is not a single hidden substance or one dramatic mineral deposit. It finds a pattern of evidence built from light, rock fragments, and excavated terrain. The far side is understood through materials that either remain exposed on its surface or arrive on Earth after violence has launched them free. That evidence shows an old feldspar-rich crust, scattered volcanic contributions, and deeper hints exposed by large impacts. In this region of the story, the hidden hemisphere becomes tangible not through abundant returned stones, but through the patient reading of matter at a distance until its ancient outer composition takes clear and measured form. The South Pole-Aitken basin is more than an enormous hollow in the lunar far side. It is also one of the best natural windows into the moon's deeper layers. Most of the lunar surface shows only the upper crust, modified by impacts, covered by regolith, and altered by long exposure to space. A giant basin changes that condition. When an impact reaches sufficient size, it does not simply disturb the surface, it excavates downward through large volumes of crust, uplifts buried material, and redistributes rock across a wide region. This makes the basin scientifically valuable in a special way. It may expose or at least bring closer to the surface rocks that usually remain hidden far below the ancient highlands. To understand why this matters, it helps to picture the moon as a layered body. The outer crust forms the visible shell. Beneath it lies deeper crust, and below that lies the mantle, a thicker region made of denser rock. The exact boundaries and compositions are not identical to Earth's, but the general layered structure remains central to lunar science. The upper crust is easier to study because it is at the surface. The lower crust and upper mantle are harder to reach. No human drilling on the moon comes close to those depths. Scientists therefore depend on natural excavation. Large impacts are the moon's deepest probes. Of all nearby lunar structures, the South Pole-Aitken basin is among the strongest candidates for having disturbed the crust deeply enough to reveal material from far below the ordinary surface. This possibility has guided decades of study. If the basin exposes lower crust or upper mantle material, then it offers clues to how the moon differentiates early in its history. Differentiation is the process by which a world separates into layers based on density and chemistry, while it is still hot enough for materials to move. In the moon's early magma ocean stage, lighter minerals rise to form the crust, and denser materials remain below. If scientists can identify rocks from deeper levels, they can test models of this early separation. They can ask whether the lower crust differs strongly from the upper crust, whether mantle material reaches basin floors or central uplifts, and how giant impacts mix these layers together. In this sense, the basin is not only a scar, it is a rare access point to the moon's buried interior history. Remote sensing has provided important evidence, though not a final answer in every detail. Spectral observations of parts of the South Pole-Aitken basin show mineral signatures that differ from typical far-side highlands. Some regions contain more mafic material, meaning rock richer in iron and magnesium than the feldspar-dominated upper crust. Mafic rocks are generally darker and denser than anorthositic crust. Their presence can suggest excavation from deeper layers, volcanic deposits, or impact-related melt. The difficulty is that these possibilities can overlap. A mineral signature alone does not always prove whether a rock comes from lower crust, upper mantle, or later volcanic infill. Even so, the basin consistently appears compositionally distinct enough to support the idea that it samples material not commonly visible elsewhere on the far side. Impact melt adds another layer of complexity. In a collision large enough to form the South Pole-Aitken basin, enormous volumes of rock would melt. Some of that melt would pool, cool, and later become part of the basin floor or surrounding deposits. This means the basin does not present a clean cut through lunar layers in the way a laboratory slice might. It is more like a violent mixing zone where uplifted crust, excavated deep material, impact melt, and later volcanic deposits may all coexist. That is why interpretation requires caution. Observations indicate access to unusual and possibly deeper materials, but it remains uncertain exactly how much of the present basin surface comes directly from the lower crust or upper mantle, and how much reflects impact-generated reworking. Even with that uncertainty, the basin remains one of the most promising targets for understanding the Moon's interior. The scale of the excavation alone makes it difficult to dismiss. A structure more than 2,500 kilometers across and several kilometers deep relative to its surroundings must affect the crust profoundly. Models of impact physics suggest major thinning of the crust beneath the basin. Gravity data support this view, showing structural differences below the surface that align with massive excavation and long-term adjustment. In some studies, dense material beneath parts of the basin has been interpreted as evidence of uplifted mantle, a concentration of impact-related melt, or material associated with the original impactor. These interpretations differ in detail, but they agree on one central point. The basin is deep enough and unusual enough to reveal something about the Moon's interior that ordinary terrain does not. Crater-central peaks and inner rings within and around the basin add to this inward view. When large impacts occur inside the basin later in lunar history, they excavate again into already disturbed ground. This creates a layered opportunity. A younger crater inside an ancient giant basin may bring up material that has already been structurally altered or uplifted by the earlier basin-forming event. In this way, the South Pole-Aitken region becomes a nested record of excavation. One deep wound is later sampled by smaller, younger wounds. The basin therefore acts not only as a single window, but as a geological field in which multiple openings into subsurface material appear over time. The basin's far side location makes it even more important, because the far side generally has thicker crust. A giant impact there is especially valuable. It cuts into a substantial outer shell that otherwise preserves ancient highland material across wide distances. If even this thick crust is breached or strongly thinned in the South Pole-Aitken region, then the basin becomes one of the only places where deeper lunar structure may approach observational reach. Without such a feature, much of the far side would remain compositionally dominated by the upper crust alone. The basin interrupts that dominance. It creates a rare inward opening in a hemisphere otherwise defined by preserved outer layers. NASA's interest in this region reflects that scientific promise. Orbital data from missions such as Lunar Prospector, the Lunar Reconnaissance Orbiter, and the Gravity Recovery and Interior Laboratory strengthen the case that the basin is central to understanding lunar interior structure. Composition maps identify unusual materials. Topographic data define the basin's great depth and extent. Gravity measurements reveal hidden differences in subsurface mass. Together, these do not solve every question, but they narrow them. The basin is not an ordinary depression. It is an ancient excavation with the potential to preserve evidence of lower crustal or mantle-related material. This is why the South Pole-Aitken basin is often discussed as a major target for future sample return. A carefully selected sample from within this region could help resolve whether the detected mafic materials are lower crust, upper mantle, impact melt, or some mixture of all three. It could provide ages tied directly to the basin-forming event or to later volcanic and impact activity within the basin. Such a sample would connect remote sensing to laboratory certainty in a way not yet fully achieved. For now, the evidence remains strong but partly indirect. The window is open, but not yet fully entered. What NASA finds here is one of the far side's deepest scientific possibilities. The hidden hemisphere contains a basin so large that it may expose layers of the moon usually buried beyond reach. The surprise is not only the basin's size, but the way it turns a remote landscape into an interior clue. In this region, the far side becomes more than a preserved ancient surface. It becomes a place where the moon may have opened itself, however imperfectly, and allowed its deeper structure to come closer to light. At the far side's southern edge, the surface descends into one of the coldest environments anywhere near Earth. Here, near the lunar South Pole, sunlight behaves in an unusual way. Because the moon's axis is tilted only slightly relative to its orbit, the sun never climbs high above the horizon at the poles. Light moves in long, shallow arcs. High ridges, crater rims, and uneven ground cast shadows that can persist not for hours, but for immense spans of time. In some deep polar craters, sunlight may not reach the floor at all. These are called permanently shadowed regions. They're not shadowed because night there never ends in the ordinary sense, but because the low angle of the sun keeps certain depressions hidden from direct illumination throughout the lunar year. On the far side, some of these cold traps lie within terrain that is already remote, cratered, and ancient, making the polar region one of the most inward and delicate parts of the moon's hidden hemisphere. A cold trap is exactly what the name suggests. It is a place cold enough to hold volatile material for very long periods. Volatiles are substances that can evaporate or escape easily under warmer conditions. On the moon, the most important volatile in this context is water, especially in the form of water ice. At most places on the lunar surface, exposed water molecules do not last long. Sunlight heats the ground strongly during the long lunar day, and the moon's lack of a substantial atmosphere gives little protection. Molecules can break apart, escape into space, or migrate across the surface. In a permanently shadowed crater, however, temperatures can remain extremely low enough for water molecules and other volatiles to accumulate and survive in frozen form. Over time, such regions may become quiet reservoirs of ice mixed with dust and regolith. NASA and other missions gather increasing evidence that water ice exists in these shadowed polar zones. Instruments aboard spacecraft detect signs consistent with surface frost or subsurface ice, though the exact amount, distribution, and physical form vary from place to place and remain subjects of active study. Some observations come from neutron measurements, which can indicate the presence of hydrogen, an important clue because hydrogen is a major component of water. Other observations come from reflectance measurements and thermal data. NASA's Lunar Reconnaissance Orbiter, for example, helps map temperatures and illumination conditions in polar craters with great precision. These measurements show that some parts of the lunar South Pole remain cold enough to preserve ice over geological timescales. On the moon's far side polar region, that finding adds an entirely new layer to the hidden hemisphere. The far side is not only a place of ancient rock and impact history, it is also a place where frozen material may persist in darkness. The source of this water is likely mixed. Some may come from comet impacts, which can deliver water and other volatiles to the lunar surface. Some may come from water-bearing asteroids. Some may be produced by interactions involving the solar wind, a stream of charged particles flowing outward from the Sun. When hydrogen from the solar wind interacts with oxygen-bearing minerals in lunar soil, small amounts of hydroxyl or water-like compounds can form. These molecules may then migrate across the surface in a hopping process driven by temperature changes, eventually becoming trapped in cold polar shadows. Observations indicate that more than one process probably contributes. It remains uncertain how much each source provides, and how much ice lies as clean deposits versus how much is mixed grain by grain into dusty soil. The far side South Polar region is especially important because it combines cold traps with the immense geological significance of nearby terrain. Parts of the South Pole-Aitken basin extend into this broader region, meaning that ancient impact structure and polar volatile preservation meet in the same large landscape. This does not mean every shadowed crater there is rich in accessible ice. The Moon rarely offers uniform distributions of anything. Illumination changes from ridge to hollow. Surface roughness matters. Local slopes matter. The age and shape of each crater matter. But the overall scientific picture is strong. The far side polar region contains some of the best natural settings on the Moon for preserving frozen volatiles. The physical state of this ice matters as much as its presence. In some places it may occur as thin surface frost. In others it may be buried beneath a dry upper layer of regolith. In still others it may exist as scattered grains mixed through the soil. This uncertainty affects both science and exploration. A buried deposit tells a different story from a clean sheet of surface frost. Buried ice may preserve a longer climate and impact record. Surface frost may respond more readily to changing illumination or micrometeorite gardening. Gardened in this sense means slowly churned and mixed by constant small impacts. The far side polar region therefore acts not only as a freezer, but as a layered archive where ancient delivery, migration and preservation processes may be recorded in frozen material. Temperatures in these permanently shadowed regions are among the lowest measured in the solar system for sunless natural surfaces. Without direct sunlight, and with no atmospheric blanket to carry warmth downward, some crater interiors remain extraordinarily cold. This thermal isolation is why the ice can survive. It also makes these regions physically challenging to study. Darkness is constant. Communication from the far side is already difficult because the Moon blocks direct radio contact with Earth. At the polar far side, steep terrain and long shadows add further complexity. A spacecraft or rover operating there must contend with limited solar power, harsh cold, and the need for relay communication. These conditions make every measurement hard-won. Yet the scientific reward is considerable. Water ice on the Moon matters for understanding how volatile materials move through the inner solar system. It also matters for future exploration, since water can support life support systems and be separated into hydrogen and oxygen for fuel and breathing supplies. In this script, however, the deeper significance remains scientific rather than logistical. The far side's frozen shadows preserve matter that cannot survive on the bright open surface. They reveal that the Moon is not only dry rock under sunlight. In selected hidden hollows, it is also a collector of rare molecules arriving over immense spans of time. NASA's findings here remain careful rather than absolute. Observations strongly support the presence of water ice in permanently shadowed polar regions, including areas associated with the South Polar far side. It remains uncertain how pure, thick, continuous, or easily reached many of these deposits are. Some may be patchy, some may be deeply mixed into regolith, some may differ greatly from crater to crater. but the general conclusion is now central to lunar science. The Moon's cold polar shadows can preserve water ice, and the far side South Polar region is one of the most important settings in which this preservation occurs. What NASA finds in this inner region of the hidden hemisphere is a quiet contrast to the battered highlands above it. In deep craters where sunlight does not enter, the far side holds not only ancient stone but frozen traces of passing bodies and wandering molecules. The surprise here is not dramatic movement or visible abundance, it is endurance. In places of permanent darkness, the Moon keeps delicate material safe across ages, turning shadow itself into a form of storage. On the far side, where vision once failed entirely, some of the most important discoveries now lie in the coldest darkness of all. The far side of the Moon is shaped not only by rock, ice, and ancient impact history, but also by a rare environmental condition that exists because of simple geometry. When the Moon stands between Earth and the far side surface, it blocks a large share of the radio noise produced by human civilization. Radio noise in this sense means the constant flow of signals sent outward by broadcasting systems, radar, satellites, and many forms of electronic activity on Earth. These signals spread through space and can interfere with sensitive instruments designed to study the universe at radio wavelengths. On the near side of the Moon, that interference remains present because Earth stays above the horizon for much of the time. On the far side, Earth is physically screened by the lunar body itself. Rock becomes a shield. The result is the most radio-quiet large region near Earth. A place where the hidden hemisphere offers not only geological difference, but a distinct observational environment. This quiet matters because the universe speaks in many kinds of light, and radio waves are one of them. Radio waves are a form of electromagnetic radiation with wavelengths longer than visible light. Many cosmic processes produce them, charged particles spiraling through magnetic fields, gas clouds in galaxies, exploding stars, jets from black holes, and the faint structure of the early universe can all be studied through radio signals on Earth. Radio astronomy is possible and often highly successful, but it is also increasingly challenged by human-made interference. Even in protected desert regions or remote mountain sites, signals from aircraft, satellites, ground transmitters, and other technologies can intrude. The far side of the Moon offers a natural refuge from much of that interference, because the Moon itself blocks the line of sight to Earth. This shielding is especially valuable for low-frequency radio astronomy. Low-frequency radio waves are difficult to study from Earth for two main reasons. First, Earth's ionosphere, a charged upper region of the atmosphere, can reflect or distort some long-wavelength radio signals. Second, human technology produces strong radio contamination at many useful frequencies. On the far side of the Moon, there is no thick atmosphere, and therefore no ionosphere like Earth's to create the same barrier. There is also no direct Earth radio glare in the shielded region. This makes the far side uniquely attractive for observing the low-frequency universe. Scientists have long recognized this potential. It is one of the most remarkable features of the hidden hemisphere, even though it is invisible in ordinary photographs. The value of this radio darkness reaches into some of the deepest questions in astronomy. One major goal is the study of the cosmic dark ages and the cosmic dawn, early periods in the history of the universe before and during the formation of the first stars and galaxies. These eras leave subtle signatures in low-frequency radio emission, especially from neutral hydrogen. Neutral hydrogen is ordinary hydrogen, whose electron remains bound to its proton rather than being stripped away. Its signals can, in principle, reveal how the universe changes from darkness into the first widespread light of stars. These signals are extremely faint and difficult to isolate. A radio-quiet environment is therefore precious. The lunar far side offers one of the best natural sites in the inner solar system for such work. The far side also supports the study of the Sun and of planetary space environments. Solar bursts, space weather activity, and interactions between charged particles and magnetic fields can all generate radio emissions. Instruments placed on the far side, especially at low frequencies, could observe some of these phenomena with reduced terrestrial interference. In addition, the far side could help astronomers search for radio signals from magnetized exoplanets, study the structure of our galaxy, and probe energetic events across cosmic distances. The key advantage remains constant. By blocking Earth's radio emissions, the Moon creates an observational silence that does not naturally exist on our planet. This silence is never complete in an absolute sense. The far side is not free from all noise. Spacecraft in lunar orbit can produce emissions. Solar activity can create its own radio environment. Cosmic sources themselves overlap in the sky. Future human activity around the Moon could also threaten the quiet if not carefully managed. But compared with almost any other nearby location, the far side remains extraordinarily shielded. Observations and modelling consistently support this conclusion. It is quiet not because nothing happens there, but because the largest nearby source of technological interference, Earth, is hidden below the lunar horizon. There is a certain scientific elegance in this. The same tidal locking that once keeps the far side hidden from human view now gives it one of its greatest modern values. The hemisphere that cannot be observed directly from Earth becomes the hemisphere from which Earth can best be excluded. The Moon's bulk, which once blocks vision and communication, also blocks noise. What begins as a limitation becomes an advantage. This is one of the far side's most surprising truths. Its hidden nature is not only historical, it is functional. The very fact that it turns away helps make it a place for deeper listening. NASA and other institutions have studied this possibility for years through mission concepts, technology development, and broader discussions of lunar science priorities. Small future radio instruments, distributed antenna arrays, or more ambitious far-side observatories have all been considered as ways to use this environment. Some proposals focus on low-frequency cosmology. Others focus on heliophysics or planetary radio science. The exact form of a future observatory remains uncertain because such projects face major engineering challenges. Instruments must survive the harsh thermal environment, communicate through relay systems, and operate on difficult terrain far from direct Earth contact. Yet the scientific case for the far side's radio quiet remains strong regardless of how quickly such observatories are built. This radio darkness also has a protective meaning. It is not an unlimited resource. If the far side becomes heavily occupied by noisy equipment, constant traffic, or poorly managed transmissions, its unique scientific value could be diminished. For that reason, discussions of future lunar activity increasingly include the idea of preserving radio quiet zones on or above parts of the far side. The issue is not only technical, it reflects a broader recognition that some environments are valuable precisely because they remain undisturbed. On the Moon's far side, quiet is a measurable scientific asset. In this region of the story, the hidden hemisphere is no longer only a record of ancient lunar history. It becomes a setting for future discovery about the wider universe. Its craters and basins still matter. Its ice-bearing shadows still matter. Yet above and around them lies another form of significance, one based not on what the surface contains, but on what it blocks. The moon's far side makes room for faint signals by standing in the way of louder ones. That is a rare gift in a noisy technological age. What NASA finds here is therefore not an object on the far side, but a condition created by the far side itself. The surprise lies in the silence. A nearby world of dust and stone turns out to provide one of the best places near Earth for hearing the weak radio murmur of the cosmos. In the inward path of this hidden hemisphere, that silence becomes one of its deepest scientific features, as real and valuable as any basin, ridge, or frozen crater floor. To work on the moon's far side, spacecraft must solve a problem that does not exist in the same way on the hemisphere facing Earth. The moon itself blocks direct communication. A signal sent from the far side cannot travel straight through rock to reach Earth. This means that exploration there depends on relay systems, careful orbital planning, and a style of operations shaped by distance and interruption. In this region of the story, the far side is seen not only through its geology, but through the methods required to reach it. NASA's understanding of this hidden hemisphere grows through orbiters above it, remote instruments aimed across it, and mission planning shaped by the fact that the far side cannot simply call home on its own. This communication barrier is fundamental. A relay spacecraft is an intermediate messenger placed where it can see both the far side surface and Earth. Without such help, a lander or rover operating on the hidden hemisphere would fall silent whenever the moon blocked the line of sight. This is one reason the far side remains harder to explore than the near side. On the near side, direct radio contact is usually possible. On the far side, communication architecture becomes part of the science. Every image, temperature reading, mineral map, and terrain measurement depends first on the ability to move information across space in stages. The hidden nature of the far side therefore continues into the practical present. It is still a place reached through indirection. NASA has not yet placed astronauts on the lunar far side, and no far side sample returned by NASA has yet transformed the region the way Apollo transforms the near side. Even so, NASA has learned a great deal through orbital missions that repeatedly pass above the hidden hemisphere. Orbiters do not need to land to gather important evidence. They map topography, measure reflected light, detect temperature, trace gravity variations, and image the surface in fine detail. The Lunar Reconnaissance Orbiter is especially important in this regard. It provides detailed images of far-side craters, basins, ridges, slopes, and polar-shadowed regions. Its laser altimeter builds precise elevation maps. Its thermal instruments help identify cold traps near the poles. Through repeated passes, the far side becomes increasingly measured, even when its surface remains untouched by human boots. The Gravity Recovery and Interior Laboratory mission adds another kind of insight. Rather than focusing mainly on visible terrain, it measures tiny changes in the motion of paired spacecraft caused by differences in the moon's gravity field. From these measurements, scientists infer buried structures, crustal thickness variations, basin-related mass anomalies, and the hidden consequences of ancient impacts. This is especially valuable on the far side, where giant structures such as the South Pole-Aitken basin and the global contrast in crustal thickness demand more than visual interpretation. Through gravity mapping, NASA learns not just what the far side looks like, but how mass is arranged beneath it. The hidden hemisphere is therefore explored both from above and below in an indirect sense, through image and gravitational response together. Relay-based exploration becomes even more visible in missions conducted by international partners. China's Chang'e 4 mission, which lands in the South Pole-Aitken basin in the year 2019, demonstrates successful far-side surface operations using the Queqiao relay satellite. This is not a NASA mission, yet it becomes part of the modern scientific picture that NASA studies alongside its own findings. The lander and rover return direct observations from a far-side location, including terrain images, local composition measurements, and environmental data. The mission confirms that sustained surface work on the far side is possible when relay support is in place. It also strengthens interest in the basin as a scientifically rich site where ancient crust, impact history, and deeper material may be studied in combination. For NASA, such missions help refine priorities for future work. A far-side landing is not only a matter of reaching the surface safely, it is also a matter of selecting the right terrain, maintaining communication, surviving extreme temperature changes, and coordinating orbital and surface assets. The far side's geology makes these choices especially important. A basin floor, a highland rim, a polar shadow boundary, and a radio-quiet flat plane each serve different scientific goals. The hidden hemisphere therefore demands a joined approach in which engineering and science guide one another closely. The route to knowledge is not separate from the terrain, it is built by the terrain. The far side also teaches caution in how remote measurements are interpreted. Orbital data are powerful, but they have limits. A mineral signature seen from above may reflect a thin surface layer rather than deep composition. A slope that appears smooth in one image may be hazardous at landing scale. A dark patch may represent basalt, impact melt, or mixed regolith that needs closer study. This is why surface missions remain so valuable. They calibrate orbital knowledge against direct local measurement. A rover can examine grain size, rock texture, chemistry, and small-scale relationships that an orbiter cannot fully resolve. In this way, each successful far-side mission sharpens the meaning of all the data that come before it. The communication problem continues to shape future plans. Any NASA far-side lander, rover, drilling platform, or observatory would require relay capability unless supported from a suitable lunar orbital system. That requirement affects cost, timing, mission complexity, and risk. It also shapes what kinds of science can be done. A simple stationary lander may be easier to support than a long-range rover. A radio observatory on the far side would need especially careful protection from contamination by its own support systems. A polar mission would need to balance relay geometry with lighting conditions and terrain hazards. These are not separate technical footnotes. They are part of what the far side is. Its physical orientation creates an operational environment unlike the one on the near side. Yet the same barrier that complicates exploration also enriches scientific value. The Moon's body blocks radio noise from Earth, preserves undisturbed shadowed ice in some craters, and shields ancient terrain from the dense traffic of early human exploration. Because the far side is harder to reach, it remains in some ways more pristine as a field site. That does not mean it is untouched by impacts or time. It means it has been less altered by human presence and less sampled directly. Each modern mission therefore enters a region still carrying a high ratio of unknowns to direct ground truth. For scientists, that is both a challenge and an opportunity. NASA's growing knowledge of the far side is thus cumulative and collaborative. It comes from American orbiters, from international surface missions, from Earth-based analysis of remote data, and from mission designs that treat communication as a central scientific condition rather than a background technical matter. The far side is no longer invisible, but it is still not ordinary terrain. It requires an architecture of support that mirrors its physical hiddenness. To explore it is to work with distance, blockage, and delay. What NASA finds in this region of the far side is therefore inseparable from how the far side must be reached. The surprise is not only in the craters, the basin floor, or the frozen shadows. It is also in the method. A nearby hemisphere still requires indirect vision, relay voices, and repeated passes from orbit before it yields its details. In this way, the far side remains true to its nature. Even in the age of advanced spaceflight, it is explored through patience, geometry, and careful connection across a barrier of stone. What NASA finds on the moon's far side is not one hidden object waiting in darkness. It is a connected set of differences that turn the far side into a distinct scientific world within the same moon. The surprise lies in how many of these differences join together. The far side is brighter because ancient highland crust remains widely exposed. It is more heavily cratered because less later volcanism covers that old terrain. It contains fewer maria because its crust is thicker and its internal heat-producing materials are less concentrated than on the near side. It holds one of the largest known impact basins in the solar system, a structure so immense that it may open a path toward deeper lunar layers. At its polar edge, it preserves permanent shadows cold enough to trap water ice. Across its broad hidden surface, it also creates a radio-quiet environment unlike any other nearby place. Each of these discoveries matters on its own. Together, they reveal a hemisphere that is not simply the other side of the moon, but a record of the moon's uneven evolution from outer surface to inner structure. The broadest lesson is asymmetry. The moon appears simple from Earth, a rounded body with a familiar face, yet its two hemispheres do not share the same geological expression. On the near side, large dark basalt plains dominate much of the visible pattern. On the far side, bright cratered highlands remain in command. This difference is not superficial. It reaches from surface brightness to crustal thickness, from volcanic history to thermal evolution, from basin structure to chemical distribution. The moon is one body, but its history is not written evenly. The far side preserves this truth with unusual clarity because it retains more of its ancient exterior. NASA's findings help show that appearance, structure, and chemistry belong to the same story. The old bright crust of the far side is not just visually different, it reflects a thicker outer shell rich in feldspar-bearing highland rock. The scarcity of dark volcanic plains is not simply a missing surface feature. It is evidence that magma finds fewer easy routes upward and that internal heat is less concentrated there. The great abundance of craters is not just rough scenery. It is record preserved because widespread lava floods do not erase the older surface in the same way they do on the near side. The South Pole-Aitken basin is not only a gigantic scar, it may be a natural excavation into deeper lunar levels, where the lower crust and perhaps material influenced by the upper mantle become more accessible to study. The far side's polar shadows are not merely dark places, they are cold traps where water ice may survive for immense spans. Its radio silence is not emptiness. It is a rare environmental condition created by the moon's own bulk blocking Earth's noise. One finding leads into the next. The far side becomes scientifically powerful because many lines of evidence converge there. This convergence also changes the meaning of surprise. Popular imagination often expects the hidden side of the moon to contain something singular and dramatic, some isolated discovery that overturns ordinary science. The real far side is more interesting than that, because it reveals complexity without fantasy. The surprise is that a nearby world can remain familiar in outline yet differ so deeply in substance from one hemisphere to the other. The surprise is that a single moon can preserve both a more volcanic face and a more ancient face. The surprise is that quiet orbital geometry can produce not only centuries of concealment, but also one of the best radio-shielded environments near Earth. The far side is surprising not because it breaks known physics, but because it expresses planetary history in a more uneven and revealing way than simpler expectation suggests. Yet important uncertainties remain. Observations indicate that the far side's crust is thicker, but the full origin of that asymmetry is still studied. Early heating from Earth, magma ocean crystallization patterns, giant impacts, and later internal evolution may all play roles in different proportions. Observations indicate unusual compositions within the South Pole-Aitken basin, but it remains uncertain exactly how much of that material comes directly from the lower crust or upper mantle, and how much reflects impact melt or later volcanic processes. Observations strongly support water ice in permanently shadowed polar regions, but the precise abundance, purity, grain size, and accessibility of these deposits vary and are not yet fully known. The near-side concentration of creep and the far-side relative depletion are well supported, yet the exact sequence by which this chemical contrast emerges is still being refined. The far side therefore stands as both a solved pattern and an unfinished investigation. The large structure of the story is clear. Some of the deeper mechanisms remain open. This mixture of understanding and uncertainty is part of the far side's scientific value. A world is most useful to study when it's neither blank nor exhausted. The moon's far side is no longer invisible, yet it is far from fully sampled. Orbital missions provide images, topography, temperature maps, gravity fields, and compositional measurements. These reveal major truths with confidence, but remote sensing always leaves some questions unresolved. Surface missions, drilling, carefully chosen sample returns, and long-duration observatories could sharpen the picture greatly. A sample from the South Pole-Aitken basin could test ideas about deep lunar structure. Polar sampling could clarify the form and history of ice deposits. A preserved radio-quiet site could open new windows on the low-frequency universe. The far side remains a place where future work can still change the depth of understanding, even if the broad outline is already known. In the end, what NASA finds on the moon's far side is a hemisphere that gathers many of the moon's most important scientific themes into one concealed geography: ancient crust, thick outer structure, sparse volcanism, giant impact history, frozen polar shadows, and observational quiet all meet there. The far side is the moon's preserved memory and its inward-facing laboratory. It shows how planetary bodies can be shaped by unequal cooling, unequal chemistry, and unequal resurfacing without ceasing to be single worlds. It shows how hiddenness can become scientific power once instruments finally arrive. Most of all, it shows that the moon still rewards careful looking. A world seen by humans for all of history still contains a hemisphere whose full meaning only emerges through patient modern measurement. The far side remains calm in appearance. Its bright highlands, crater chains, shadowed basins, and silent horizons do not announce themselves loudly. But NASA's work reveals their joined significance. There, in terrain once known only as absence, lies a complete pattern of lunar difference. It is this pattern, more than any single object, that forms the true surprise. The hidden hemisphere turns out to be one of the clearest places where the moon explains itself. The moon continues its orbit in silence, keeping one face toward Earth and one face turned away. What once seems like a simple hidden half becomes, through careful study, a preserved record of ancient crust, giant impacts, uneven heat, scarce volcanism, frozen shadow, and rare quiet for listening outward into space. The far side does not reveal a single secret object. It reveals a structure of differences, each one connected to the others, each one helping explain why this nearby world is not the same across its two hemispheres. Its bright highlands remain exposed because broad lava floods do not cover them as they do on much of the near side. Its great basin near the South Pole carries the force of an impact from the earliest age of the solar system. Its deeper shadows hold cold so steady that water ice may endure there for ages. Its surface, once unreachable to sight from Earth, now stands mapped in height, composition, temperature, and gravity. Even so, much of its meaning still rests in patient interpretation. Some rocks hint at deeper layers, some chemical patterns suggest early processes not yet fully resolved. Some frozen deposits remain measured at a distance, waiting for closer touch. The far side, therefore, remains calm, ancient, and unfinished in the best scientific sense. It is no longer unknown, yet it is not exhausted. It still keeps questions within its craters, beneath its dust, and inside its thick old crust. Under long sunlight and long night, it continues as it has for billions of years, carrying the marks of collision, cooling, and time. In that steady stillness, the hidden hemisphere becomes less a place of mystery and more a place of deep record, where the moon's long history rests quietly in stone, shadow, and silence.